Okay, perfect. Cool. Yeah, so thanks a lot, Yamila, and hello also from my side. We already had a lot of interferometry talks at this conference, and some also related to gravity. So now I wanted to highlight a bit the capabilities of gravity to search for and characterize exoplanets. As you can see, I'm part of the exogravity team, and we're quite a large collaboration with great people from all over the world. And I just wanted to mention also that we're always welcoming new members, especially also young scientists who are interested in exoplanets and interferometry. So please always feel free to reach out to us. So I wanted to start my talk with this plot here that's showing the contrast versus the separation of some known transit, radial velocity, and imaging planets, as well as a simulated population of mature, young, and very young giant planets underneath. And I think it nicely shows here this blue region that with gravity, we are now significantly expanding the parameter space where we can directly detect exoplanets towards much smaller angular separations. And this, for example, brings us closer to this population of the radial velocity planets. In fact, we have already directly detected one of them, Beta Pictoris C, and I will talk about this a little bit more detailed later. So how does gravity achieve this additional gain in angular resolution? Of course, gravity is an interferometer, so it combines the light of multiple telescopes simultaneously. In our case, it's the 4 8-meter telescopes at Paranal. And as you can see, there's a lot going on. But the most important thing for our exoplanet observations is that gravity has 2 beam combiners, which basically means that there are 2 interferometers that we can use. One to observe the bright host star. In this case, it's GQ Lupi A with the fringe tracker. And then the other one to observe the faint companion, in this case, GQ Lupi B with the science spectrograph. And then when we look at the optical path difference that we can measure between these interferometric fringes, you can work out the relative astrometry of the 2 objects with a very high precision. In the case of our exoplanet observations, this is usually at least 100 microarc seconds astrometry, but often even better than that. So it's at least, a factor of 10, maybe even 20 times better than what other facilities can do at the moment. On the other hand, from the contrast of these interferometric fringes, we can learn something about the spectrum of the planets. In fact, we can obtain a K-band spectrum of the resolution of about 500. And you can see at this resolution, we start to see CO absorption features at 2.3 microns. And this can ultimately then tell us something about the formation history of these objects. So we're trying to make use of these unique capabilities of gravity and observe 10 high contrast exoplanetary systems as part of the exogravity large program. And you might already have seen some of our results over the last 2 or 3 years or so, but today I really want to focus on 2 systems. And the first of the 2 is Beta Pictoris, which is one of the oldest directly imaged exoplanets, Beta Pictoris B, that orbits almost in like an edge on orbit in this inner cavity of a large debris disk, as you can see in the figure here. But in 2019, Anne-Marie Lagrange et al., they announced evidence for an additional companion in the system based on radial velocity data. And in fact, only about half a year later, we were able to directly detect this additional companion, Beta Pictoris C, with gravity. And this really was the first direct detection of a radial velocity planet and was enabled by the unprecedented angular resolution that we can achieve with gravity. As you can see, it wasn't an easy detection because the field of view of these gravity optical fibers is only about 50 by 50 milliarc seconds or so. So it's a really tiny field of view. And we had to pinpoint the location of Beta Pictoris C based on the RV data from Anne-Marie and her collaborators so that we were able to find it. Now, after taking a few astronomical data points of both Beta Pictoris B and also C with gravity, we of course could improve the constraints on their orbital parameters. And in fact, also we now start to be able to see the gravitational influence of one planet onto the other planet in the system. So especially here on the left-hand side, you can see the orbit of Beta Pictoris B, and you can see the Keplerian residuals at the bottom. And as you can see, there's a clear systematic offset from a Keplerian orbit, which is caused by the gravitational influence of the other planet in the system by Beta Pictoris C. And from this offset, we can now work out, for example, the orbital period, but also the mass of Beta Pictoris C. And I think that's really an exciting result that we can now measure orbits such a high precision. And this also, of course, gives us an independent dynamical mass constraints for both of these planets that also places C in the planetary mass regime. And we can use these independent mass constraints to compare them with evolutionary models, and try to understand how these planets formed. And you can read more about that in a very good paper from Matthias Nowak in 2020. The other system that I want to talk about is HD26893, which is fairly similar in its architecture to Beta Pictoris. There's also two companions in the inner cavity of a large outer debris disk. The B companion has been studied already extensively with gravity, sphere, and GPI. There's many good characterization papers about it. Then there's a C companion that has been predicted to exist mostly from a Gaia proper motion anomaly, but it lacks direct evidence. And then there's also perhaps another planet in the gap of the debris disk, but this is yet to be confirmed. I think there's also a James Webb program that will try to find this outer planet. So let's focus a bit on the inner two objects and this Gaia proper motion anomaly. So what's happening here is that the B companion, who has, as I said, been studied extensively and whose orbit you can see here, is moving sort of towards the northwest, so positive declination and negative right ascension. And that means that the host star should make a reflex motion in the opposite direction. So negative declination and positive right ascension. So sorry for the axis swap here between the two figures, but the orange vectors are indeed in opposite directions. And the magnitude of this motion should depend on the mass ratio between B and the host star, and could lie anywhere along this projection here, which is shown in blue. However, the Gaia proper motion anomaly measurement is shown by the blue ellipse down here with uncertainties as well. And you can see it's clearly not compatible with that B-only scenario. And this is why first Grosjean et al. 2019 thought that there has to be another closer in companion, which was called the C companion. This is also not sensitive to the D1 out in the, that could be in the debris disk gap, because it's at too long separation, and this Gaia anomaly is not sensitive to these far separations. So yeah, I please ask you to not take any screenshots or share anything on social media about this result, because it's still preliminary and we're working on a publication. So it's kind of confidential. But we again tried to use the Gaia proper motion anomaly together with RV data from Anne-Marie Lagrange also to predict the location of the C companion. But this time it was a lot more difficult because we had to search a much larger region for that object. But then after we tried 9 different pointings with gravity, we were finally able to also get a direct detection of the C companion at only about 110 milliarc second separation. And I think that's a really, really great result, because firstly, it kind of demonstrates that we can now use, for example, Gaia data to boost the efficiency of our direct imaging searches, and even, you know, kind of try to pinpoint the location for an instrument like gravity where we have to look. And then on the other hand, it also gives us again a dynamical mass constraints on both objects in the system that place C in the planetary mass regime and B in the low mass brown dwarf regime. And I think that's also an exciting result by itself, because the mass of B had been quite unclear so far due to its extremely wet color and its very, very dusty atmosphere that was very difficult to model. So this new mass constraint is really improving what we knew before.
2 minutes, Jens.
Yeah, all good. I'm already at the last slide. So this is basically giving you an outlook into the future. So what we are trying to do there is we try to combine our gravity spectra of HD26893 and Beta Pig companions with James Webb L and M band photometry. And this will give us better constraints on the metallicity and also on the C2O ratio, especially also for the innermost planets in these systems. And from that, we can then learn something about for example, the cloud composition and the origin of this extremely red color in HD26893b, but we can also study the formation signatures and hopefully learn something about, you know, the either carbon or methane dominated atmospheres of these planets. Now, to image them with Webb, we have to use the aperture masking interferometry mode, because as I said, they're at very small separations, only about 100 milliarc seconds. So to directly detect them with Webb, we need aperture masking, because that's also giving us access to small separations and at the same time to high contrasts up to hopefully about 9.5, 10 magnitudes or so. So yeah, stay tuned for some exciting results in the future. And also thanks to the organizers for giving me the chance to talk today. And with that, yeah, I'm happy to take any questions.
Great, thanks for the nice talk. This is very exciting. So can you tell us a little bit more of how did you make the study to know where to look for this object?
Yes, sure. So yeah, for the C companion in the HG206, it was really a bit more difficult than with Beta Pictoris because the radial velocity data didn't tell us so much. It just told us that something has to be wrong and there must be another companion, but it didn't really tell us as much as for the Beta Pictoris companion. So we also added the Gaia proper motion anomaly. And what was also important is that we already had really good gravity measurements on the B companion, like the orbit of B. And by combining all of these things together and also making some assumptions that, for example, the orbits cannot cross and things like that, we kind of found a region that was small enough so we could try to find it with gravity in a couple of hours. And we were very lucky because Sasha Hinckley had some time to observe, to basically try to find this companion. And we went after it and we were lucky enough to find it. So we were very happy.
Yeah, and I think this is a great result. So there is a question by Roy. He's asking, can we look forward to a gravity spectrum of C, of the C planet, or is that beyond facility capabilities?
No, we do have a spectrum of it, but of course it's not as good as, for example, the spectrum that you have seen of Beta Pictoris B before. It's more like also the Beta Pictoris C spectrum, and it also suffers a bit from systematic problems that we are having with gravity at the very smallest separations. Sometimes we get kind of some systematic wiggles in the spectrum that also happen for Beta Pictoris C, and this is also the case in the HG26893C spectrum, I believe. But yeah, I think there will be certainly a spectrum of this in the publication.
Oh, that's great. Okay, Ryan has a question. Go ahead.
Hi, Jens. Nice talk. So quick question. Do you anticipate any challenges with, I guess, photometric calibration when combining gravity and JWST observations?
That's a very good question, I guess. Well, I think we have compared gravity with other ground-based instruments like GPI and Sphere. There we already know kind of what systematics we can expect. But of course, with James Webb, we don't have any data yet, but I expect that James Webb will be very sensitive, much more sensitive than the ground-based instruments in the L and M band. So I think that it will not be a showstopper, basically.